So here are our practice problems, and this first one, let's see if I can get it a little bit bigger here. It says find the volume of the solid formed when each figure is folded along the dotted lines. Dimensions are in inches. So on figure A, we're supposed to fold this figure up, and you can see that the top and the bottom of the figure are rectangles. So this is just going to be a rectangular solid, and it's got three different, so it's got a width of 3 here, it's got a length of 5, and a height of 2. It doesn't really matter which one you make, width or length or height, but we have 3 different measures. And so 5 times 3 times 2 would be the volume, and the volume would be in cubic inches. So we would have, that figure should look something like this box when it's all put together. So 3 times 2 times 5, and inches cubed. 2 times 5 is 10, times 3 is 30. Inches cubed should be the answer to A. The second figure here has a triangle on this base and a triangle on this base. So it's going to be a triangular prism. It's a right triangular solid, but it is a prism. And so it's going to have a triangle on the bottom, and the triangle has a width of 4 and the height of 2, and then it's got sides going up to 8. So this one is going to look very similar to my figure that I had before. When we fold it together, won't it look something like my name tag? Okay, remember my name tag was almost a triangle on the top and the bottom, and it has, we're going to call it 3 sides, even though it has this little lip. But we're going to say that's a triangle. And so our figure here is going to look very much like this when we put it together, isn't it? So again, when we have a triangle for the base, the volume will be area of the base times the height. We're pretending that's a triangle times the height. So volume is area of the base times the height, where the base is a triangle and the height is 8. So the area of the base would be 1/2 times 2 times 4. So 8 cut in half would be 4. 4 times 8 would be 32. So I drew the same triangular prism in a different configuration. So 2 times 4 would be base times height, and 1/2 of that would be area of 4. So this has an area of 4 inches squared, and then I multiply by the 8 inches, and I'm going to have 32 inches cubed would be the volume of this right triangular geometric solid, also a triangular prism. Okay, so here we are quickly sketching each figure and draw the lines of symmetry. Okay, so the first figure kind of looks like a peanut. So I've sketched a pretty good picture of the same object here, and we have some lines of symmetry, and we are not told in this one to find a point of symmetry, but there is a point of symmetry. So lines of symmetry would go from here to here, because if we folded it, assuming I had drawn it exactly correctly, I didn't. But when we fold it, it's going to be the same on the top and the bottom. So that is a line of symmetry. And also, we'll make these a little closer because they're supposed to be right on top of each other. But also, this would be a line of symmetry, because if I fold it this direction, then the two would meet. But we also have a point of symmetry. If I put a point right in the middle and I put my pencil on that point and I spun the whole thing around 180 degrees. That means I don't make a full trip around, I make a half a trip. Then this point right here would wind up being right there, and the figure would look exactly the same. So it has a line of symmetry, a line of symmetry, and then it has a point of symmetry also, because I could spin it 180 degrees and it would look the same. Now this is our next figure. It looks like, I don't know, I call them a pinwheel, but basically it's got a point of symmetry, and we could draw lines of symmetry in several places. Okay, so try to pretend with me that this is really a symmetric figure like the one you just saw. But we could split it quite a few different ways. We could make a line of symmetry going through those two leaves of the flower, right? We could make a line of symmetry going through those two leaves of the flower. We could make a line of symmetry splitting the flower in half that way, or a line of symmetry splitting the flower in half that way. And we do have a point of symmetry, because I could turn the flower 180 degrees so that this point rotated around to this point, and wouldn't the thing look just the same? Okay, so the next example or practice is, are these figures symmetric about a point, a line, or both? So this one right here, can we make a line of symmetry? Well, if we drew a line right from here through here, wouldn't the figure fold on itself? Okay, so would the figure be symmetric about that line? And this figure has no point of symmetry, because if I picked that point and rotated 180 degrees, my whole figure would be up there somewhere. Okay, if I picked that point and rotated 180 degrees, it would not look the same as it does now. So there's not a point of symmetry. I would have to completely go 360 degrees around, and that's not what symmetry is all about. So this one has no point of symmetry. Let's look at the next figure. Okay, what about this figure right here? We've got two triangles. They look like equilateral triangles put together. Wouldn't this be a line of symmetry? And wouldn't this be a line of symmetry? And guess what? Where the 2 points intersect, the two lines intersect, there's a point, and that would be a point of symmetry. This last little bit says, sometimes we can use symmetry to help us solve problems. Use symmetry to find the area of these symmetric figures. Dimensions are in meters. So if I knew the area of one little part and I multiplied it by 4, aren't all of those little pieces the exact same area? So I can find the area of the whole figure. Okay, so here's the figure, my best drawing. So they're all 4 the same size. So if we can find the area of that one little piece, we'll have the area of the whole figure if we multiply that little piece by 4. So here we have 1/2 of a circle. So 1/2, and the area of a circle is pi r squared. But then we have 4 circles, so we're going to say times 4. Well, 4 times 1/2 is 2, times pi times r squared. Well, r is the radius, it's 5, so 25. Now, there's a real quick way we can do this math, because we have 2 times 25 is 50 pi, and pi is 3.14. Okay, now let's see if you can follow this quick little way of doing it. Instead of multiplying 50 times 3.14, what if I multiply 100 times 3.14 and then cut it in half? Can I do that? 100 times 3.14 is 314, isn't it? And it's very easy to cut 314 in half, because half of, let's just do it here. So we're going to do half. 2 into 3 is 1, times 2 is 1, 11, 2, 5, 5, 10, 1, 4, 7, 157. So the area of this is 157, and the units are in meters. And it's area, so it's square meters. Wasn't that a cool trick? We could have multiplied it by 50, or we could have multiplied it by 100 and then divided by 2. Same thing. Here is the last figure that we're doing on our homework. And we're supposed to find the area of this figure. Now notice that we have a half circle joined by another half circle that's the same size. So do we really need to figure out both of them, or can we figure out the area of one part of the figure and then just double it? This one is kind of cool. Now, this is a symmetric figure. This is the same as this is. What if we drew it differently? Okay, because this part right here is 2. We know that this part right here is also 2. And since that part is 2, we know that this part is 2. In fact, if we twisted this around, we'd have a donut. So basically, we have a donut like that. Okay, so basically I'm taking this part and I'm putting it over here to complete the donut. And the donut is 2 here, and this distance here is 2, and this distance here is 2. Doesn't that look like what it is? Okay, so now it's easier to find the area of the donut than it is with the donut cut in half and made into a funny shape, because that's all that is. That's a donut cut in half and slid over. So we're going to put the donut back together to make it an easier math problem. Now, if the center of my donut is right there, see, all the way across was 2 plus 2 plus 2 is 6. Half of that is 3. So we have a big circle out here with a radius of 3. And then we're going to take out the whole of the donut. Is not part of the donut, is it? So we're going to take out the whole, which is 2 across, but it's a radius of 1. So we're going to subtract the area of the donut whole, which is a radius of 1. So if we take a big 3, radius 3 donut, and we cut out a radius 1 whole, wouldn't we have the area of that figure? So now this is 3 radius, and we have pi r squared is the area of a circle. So this one is pi 3 squared minus the area of the whole of the donut, which is pi 1 squared, which is just pi. So we have 9 pi minus 1 pi is 8 pi. And that's the area. Now, pi is an exact number, but we usually approximate it with 3.14. So the area of our whole figure is 3.14 times 8, which is 4 times 8 is 32, 8, 9, 10, 11, 24, 25, and 2 decimal places. So 25.12 square meters. I had to look and see what the units. So that's going to be 25.12 square meters. And this is a real good problem showing how we used symmetry to take a difficult looking object and turning it into a donut. That was very easy to figure out. And we have learned a lot of geometry, specifically about symmetry. And we are done with lesson 134. And this is Mrs. A. And may God bless your day.